Hello friends, hope you are having a fantastic day today. So once again, we are going to do an awesome lead code problem that has been asked at tons of companies, and it's actually a pretty fun question to solve. So without any delay, let's get started. The problem is called Koko Eating Bananas. This one is a lead code medium problem and also a very well-liked problem on lead code. Basically, we are being told that Koko loves to eat bananas. Now, Koko is a very famous gorilla, and we are given two items. We are given a piles array which contains that every single element in this array represents the number of bananas that particular pile has. And we are told that there are guards who are typically protecting the bananas, but they have gone out for 8 hours. So we are given these two items as an input. Now Coco decides to eat her bananas per hour eating speed of k, and each hour she chooses some pile of banana and then she eats k bananas. So whatever the speed we decide, she tries to eat that. If the pile has less than k bananas, then she eats all of them and will not eat any more bananas during this hour. And the most important thing is we need to return minimum integer k, such as she completes all the bananas within each hour, and we need to make sure that this k is the smallest element possible because Coco likes to eat slowly. So let's try to understand this problem with an example. So over here we are given piles. This represents that pile 1 has 30 different bananas, next one has 11, and next one has 23, and so on and so forth. And we are being told that the guards have gone for 6 hours. Okay. So now we need to figure out that in this 6 hours, what should be the speed of banana eating for Coco in order to complete every single banana in each of the pile, and also at the same time make sure that she tries to eat in the slowest speed possible. Now, one important detail is that at any given moment, Coco can only eat bananas from only one of these piles. She cannot jump around between the piles from hour to hour. So let's say that currently we have the speed of banana eating at 50 per hour. Then let's assume that in the first hour, she decides to eat 30 bananas, which means she still has time to eat 20 more bananas, but she would not go to the next pile to start eating them. She will only eat 30 and then wait for 1 hour, and during the next hour she will go to the next pile and once again start eating bananas. But once again she still has room to eat 39 more bananas, but she would not move to the next element. Okay, so maximum hours we have is 6. That is number one thing. Now let's see that what are the some of the options that we can consider. For assumption, we take the largest number in this pile, that is 30, and we say that Coco eats 30 bananas per hour. So then in how many hours will she complete eating all the bananas? So during the first hour she would complete this pile, then during the second hour she would complete this pile, and so on and so forth. In every single hour she will complete each of the piles, and then she would have still completed her banana eating in 5 hours, so less than 6. But the thing is, question is, can we go smaller than 30? That is also a question. We need to find the minimum number. So let's say that we try the second smallest element, that is 23 per hour. Then how many hours will it take for Coco to complete all the bananas? So if we do 23 hours, so k is equal to 23, then logically in the first hour she will complete 23 bananas, so she would still have 7 more bananas left in this pile to complete. So during the second hour she will also complete 7 more bananas. Then during the third hour she will complete 11 bananas. Then during fourth hour she will complete 24. Then fifth, then 4, and then sixth hour she would complete these 20 bananas. And then by the time of 6 hours she would have completed all the bananas in every single pile, and her speed would be 23, which is significantly less than the previous speed that we were considering, that was 30. Let's try to consider one more speed. Okay, let's say that instead of 23, can we go smaller than 23? So let's try 22. Okay, so if we try to do 22, then this pile would take 2 hours, this pile would take 1 hour, this pile would once again take 2 hours, and then these two piles would also take 1 hour. So if we do total sum of this actually becomes 7. So that is greater than 6, which means speed 22 is no longer feasible for Coco to eat bananas. So minimum speed she can use in order to complete all the bananas and at the slowest speed possible would be 23. And this is what the problem is actually asking us to solve. Well, brute force approach is actually quite simple because we know for sure that the maximum value has to be the maximum value that is currently present inside the given piles, because we are being told that the inputs are valid and legitimate, which means that if she eats the speed at the maximum number of bananas that are present inside the all the piles, then by that limit she should be able to complete every single one of them. But that is not going to be the ideal scenario. Maybe it might have been ideal if instead of over here, instead of this h being 8, we only had 4 hours to finish, then we have to eat at the speed of 11, but that is not the case. So what is the minimum range? Okay, so maximum range that Koko needs to eat bananas is going to be the maximum value, so 11. The minimum range can be value number 1. Okay, that let's say that in this case we actually have sum of all of these values. We have 28 hours. If we have 28 hours, then if she eats one banana per hour, then also she can complete this entire pile, but that is also not the case. So we find our maximum and minimum ranges. So logically what we can do is we can simply take every single range and then try to go over to see that if that range satisfies the property of completing the banana eating, and then we can come up with the answer. So we already know the logic. Let's say that with 1 we can complete, it would take us 28 hours to eat all the bananas, but 28 is greater than 8, which means 1 would not work. So we try to do it with 2. If we have to do it with 2, once again it's gonna take, let's say 15, so it's gonna take 15 hours, but this is also greater than 8, so 2 is also not going to work. So on and so forth. If we repeat the same process, we would find the answer 4 in this case, that this is the number of bananas she needs to eat in order to complete the entire pile. So logically this solution works as expected. Okay, that is number one thing, brute force approach. But the thing is, the time complexity in this case would be big O of n, where n is the number of the sum of all the bananas that are currently present inside the combination of all the loops. But we will try to do things slightly faster. So let's try to see that what would be the optimal approach in this case. Now, for this given example, I have actually calculated the speeds from 1 to 11 for every single hour, the banana eating speed, and I have marked that at that particular speed, how many hours will it take for Koko to complete eating all the bananas. And the important thing in this case is we need a value where we reach value number 8 at the very first time. The moment we hit very first time, that is the minimum speed Koko should eat bananas at in order to complete all the bananas within the given hours for which guards are away for. So logically, we can make a very important distinction over here, that with increase in the value of k, we can see that the value of h reduces significantly in a sorted and descending order, which means we can see that there is a descending property over here that is being maintained. Now the question is, we need to find the minimum value, but the lucky thing for us is that we actually can use the benefit of this property of this value being sorted to our advantage. What we can do is, instead of using the brute force approach where we were starting from k is equal to 1 and then just going in the linear fashion for every single bananas until we hit value number 8, we can actually use binary search in this case in order to complete this problem. Now let me show you that how doing binary search would be the greatest thing since sliced bread in this approach, because we have our minimum range, we have our maximum range, which means we know for sure that our answer has to lie somewhere between this, because any value above 11 will always yield us the result as 4. We can go even with a speed of 50 and still it is always going to give us the result as 4, which means the important thing is that once we have our left and right pointer or the minimum and maximum values, so let's mark them. So currently we have our left pointer and we have our right pointer located at these two positions. Our aim is to find the minimum value in this k that represents that h becomes 8 for the first time. And the logic is quite simple. We take L and R, we try to find the mid pointer. So we check that for this particular one, what is going to be the mid pointer? I think mid pointer is going to be this value number 6. So for value number 6, what is the total number of hours that we can use in order to generate the answer? So we can see that this value is 6. 6 is actually less than value number 8, which means this is one of the legitimate scenarios. But the question is this the minimum value we can reach 8? No, because we will need to find the value that equals to 8 at the very first moment. So then once again, now we are going to bring our right pointer one step before this one, and we will have a right pointer on this location. Once again, we will try to do the mid operation. So now if we do the mid operation, we realize that mid pointer is actually this one. So this is actually hours is equal to 10, which is greater than the target hour we had, that was value number 8, which means we will have to increase the speed in this case. So since we have to increase the speed, we will have to update our left pointer. So we will update our left pointer to come over here. Now we have two values left and right located adjacent to each other, but still we will try to find the mid pointer in this case. So in this case, if we try to take the advantage of the ceiling value, we will find mid pointer to be value number 4. Okay. And then this refers to value number 8, which means this is exactly what we are trying to find. But the thing is, we are not sure if this is the smallest value or not. So for that, what we can do is we can simply check one value adjacent to it before it to see that if that value is actually greater than or less than value number 8. If that is less than 8, which means we might have missed some values where 8 started forming, which we did not. So in this case, we know for sure that this has to be the smallest value of banana eating speed that we can use in order to finish all the bananas within the given 8 hours. Now we all know that how to calculate hours for any single pile. For that, we simply have to iterate over the given array, see that what are all the bananas are, and at that speed, how many bananas can be completed in that particular aisle. So that for that calculation, we can simply use a helper method to complete that. And basically this would yield us the complete result in order for us to find the answer. So now this is a beautiful solution for an awesome problem, and it contains one of our very near and dear species. So that's always pretty good. So now let's try to find the time and space complexity in this case. Time complexity is quite simple. It's going to be big O of log n in order to complete the binary search. And if we will also have to do some computation in order to find that how much time it takes to eat all the bananas. So let's say that becomes big O of h. But the thing is, that calculation is always going to be finite. Why finite? Because we know that the number of given input size n is going to be finite, and we will have to iterate over all the elements in order to calculate that. So that operation in itself is going to be big O of n. So in this case, the total time complexity is going to be big O of n log n, because for every single pair that we can make up until this log n time, or till that optimal period, we will have to find that how many hours it takes to calculate the results, which is going to be much faster than our brute force approach. Because in the brute force approach, we had to do this big O of n work, but we had to do it for every single possible value of k. So we were actually getting big O of n square result. And if we see space complexity, well, in this case, I just draw this additional data structure for your understanding. But actually, apart from storing few variables here and there, we don't have to use any extra space. So this is also going to be big O of 1. So this is a beautiful time and space complexity to solve this problem. Now let's see the coding solution for this one. So here is the solution. So first we are going to initialize two variables, left and right. Now for the right pointer, we will have to find the maximum value inside our given piles. So we are going to do that with using a for loop. Then we are going to run our binary search logic, where we are going to check that while left is less than right, we are going to find a mid pointer, and then we are going to call our helper method to check that whether we can finish finding the given piles using the given mid pointer or the speed that we have been able to find with the given h hours in the input. Now let's understand the logic for the can finish helper method. First, we are going to mark that the initial hours are going to be 0. And then we are going to compare that in order to complete these piles, how many hours it's going to take. So we are going to check that if the number of speed is going to be greater than any particular pile, then we can finish it in 1 hour. If not, then we need to increase the hour. If the number of hours are less than or equal to the given value h, we can determine that that speed can actually finish all the bananas. Then we need to check that whether the right pointer is equal to mid. If that is not the case, we need to find that left pointer is going to be mid plus 1. And in the end, whichever is the left pointer has to be the answer. So this solution would work as expected. And now let's try to run this code. Okay, seems like our solution is working. Awesome. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions in terms of time complexity. It is really good in terms of space complexity as well. So once again, the solution for this code is presented in our GitHub repository, so you can check it out from there. Thank you.